What's going on, everyone? Welcome back. Patrick here, and moving on with limits at infinity, we got to solve these four limits over here. And notice that they are limits at infinity because of the format that they take. We got the limit as x approaches positive infinity or the limit as x approaches negative infinity for all of these. And I'm going to show you how to solve these limits with a certain method. It's a pretty popular method. You'll probably see it come up in your textbook. Your prof is probably going to mention it. But before we get into that, I actually want to talk about a certain property first that is going to be used within the process of solving these. And the property is whenever you have the limit as x approaches plus or minus infinity of some kind of constant over x to the power of r, this is always going to equal 0. So this c value here, that's going to be some kind of real number. So that's some kind of constant, whether it's 1, whether it's 2, whether it's -5, whatever. And then this r value here, there's a couple of conditions on the r value. So the r value has to be greater than 0, because if the r value is negative, then we would be bringing it up to the numerator. And then this limit would not equal 0 anymore. So r has to be positive, has to be greater than 0. R is a rational number. So if we throw in a couple of examples, for now let's just use a constant of 1. Could be any constant, let's just use 1 for now. And then let's say we pick an r value of 1. So we'll just have 1 over x, x to the power of 1. Notice 1 is a rational number, it's greater than 0. And if we graph 1 over x, how does that look? Well, we know it looks like this. It's one of the parent functions, one of the fundamental parent functions. And notice as x is approaching positive infinity, what's the y value approaching? Well, it's approaching 0. And as x approaches negative infinity, what's the y value approaching here? It's approaching 0 as well. So notice how this property holds for that basic function. What if we had, let's pick another r value. Let's say we had 1 over x squared. How is 1 over x squared going to look like? Well, 1 over x squared looks like this, right? So again, as x approaches positive infinity, the y values are approaching 0. As x approaches negative infinity, the y values are approaching 0 as well, right? So this is always going to work out. What if we had -1 over x squared? Well, this graph would just be flipped. So it would be going that way. So we would erase these here. And notice, same thing. As x goes to positive infinity, the y value is approaching 0. As x goes to negative infinity, y value is approaching 0. Right? So this property is always going to work out. There is actually another exception. It's not too important to know, but I'll mention it anyway. X, you have to make sure when you're using this property that x to the r has to be defined. So for example, what if we have something like 1 over the square root of x? Or you could rewrite this as 1 over x to the power of a half. Notice that 1 over 2 is greater than 0. It is a rational number. But notice that the x values can't be negative because we can't be square rooting a negative. So the domain for this function is x is greater than 0. So this graph here, it actually looks like this. So there's no negative portion. There's no negative x values. And so for this function here, you could only do the limit as x approaches positive infinity of 1 over root x. That's going to equal 0. But the limit as x approaches negative infinity of 1 over root x, that actually does not exist. Okay, so there are a couple of exceptions to this. So that's why I mentioned x to the r has to be defined. And notice for this function here, the the negative x values are not defined. So this limit here would not exist. So this is not always going to equal 0, but for the most part, when we're going to be using it to solve limits, it's usually going to equal 0. So you don't have to worry about this too much. And then you could have like maybe the third root of x. This would be 1 over 3. Well, you could take the odd root of a negative x value. So this would actually look like this. So then the limit as x approaches negative infinity of this function would equal 0, while for an even root, it wouldn't exist. All right, so just be careful with that. And again, it's probably not going to come up. It's probably not even worth mentioning it, but thought I would anyway. Basically, this x to the r has to be defined. So the reason why I brought this property up is what we're going to be doing with these limits is we want to take these expressions and convert them so they're in this format. So we're going to have a bunch of expressions in this format. So let me show you what I mean with the first limit. So we got the limit as x approaches positive infinity of 4x minus 1 over 10 minus 3x. And what you want to do with these kinds of limits, I'll write it down here, is you want to divide all expressions by x to the power, the highest power in the denominator. Okay, so x to the power of highest, well, spelling highest wrong. X to the power of highest power in denominator. So not in the whole expression, just in the denominator. And notice that what is the highest power in the denominator? Notice it's going to be 1 in this case. Another way to word this is dividing everything by x to the power of the degree in denominator. Okay, so notice that what kind of function is in the denominator here? It's a linear function. So what's the degree of it? It's 1, or the highest power. Versus here we have a quadratic. What's the highest power? 2, or it has a degree of 2. So what we do is we simply take all the expressions here and divide them by x to the power 1. So we would take this 4x divided by x to the power 1. We don't have to write the 1. We would take this 1 here divided by x to the power 1. We would take the 10 divided by x to the power 1. And then we would take the 3x and divide it by x to the power 1. We took all the expressions and divided it by x to the power 1. Another way to show this is what we're doing is we're taking this numerator and we're multiplying it by 1 over x to the power 1. We're taking the denominator, multiplying it by 1 over x to the power 1. So then this expression we would, 1 over x times 4x would be 4x over x. 1 times 1 over x is just 1 over x. So we're kind of like taking this and distributing it to all the expressions, and same thing here, taking this, distributing it to all the expressions. And notice that 1 over x, that's just 1. So really what we're taking is we're taking this expression here, 4x minus 1 over 10 minus 3x, and we're multiplying it by 1. Because 1 over x is just 1. So we're actually keeping that initial expression the same, it's just in a different format now. So this is actually equal to 4x minus 1 over 10 minus 3x. This and this are the exact same thing, because we just took it, multiplied it by 1, which changed its format. It's kind of similar to when we were doing rationalization with limits, where we were adding stuff, but it's like we're multiplying by 1. So when we were multiplying it by the conjugate, for example, we were still keeping that same expression. It was just in a different format. Okay, so what happens here? Notice that we can simplify some of these. Notice that this x and that x cancel out. And so what would we be left with here? If the x's cancel out, we're just left with 4. So we'd have 4 minus, over here nothing can cancel out, so this would just be 1 over x, all over 10 over x minus, notice that these x's here cancel out, so we'd be left with a 3. And then what we can do is we can actually take this limit and distribute it to all of the individual components using the properties of limits. Hopefully you guys watched those videos already. So I'll do it for this one. I'm not going to do it for the rest, for 2, 3, and 4, just because it's kind of it's kind of like a non-important step, but just kind of want to keep it fundamental for the first one. So I'm taking this and I'm going to distribute it here, and then to all the expressions. So actually, you know what? I'll just take this limit and distribute it to all the expressions. So we'll have the limit as x approaches infinity of 4 minus the limit as x approaches infinity of 1 over x, all over the limit as x approaches infinity of 10 over x minus the limit as x approaches infinity of 3. So basically use properties of limits to go from here to here, distributed that limit to all of the expressions. And again, your prof is not going to require you to do this. This is a bit of overkill, but again, just want to show you for the first example how it works in its entirety. And now notice that we can deal with these limits here separately. So we'll have the limit as x approaches infinity of a constant. What does that equal? That just equals the constant. And then over here we'll have minus the limit as x approaches infinity of 1 over x. And notice that this, the 1 over x, is in that same format for the property that I mentioned at the beginning of the video, the constant 1 over x to the power of a rational number, which is 1 in this case. And we said that the limit as x approaches plus or minus infinity of a function in that format, that's always going to equal 0. So whenever you have a constant over x to the power of r, limit as x approaches plus or minus infinity, that's going to be 0. Same thing here, limit as x approaches positive infinity of 10 over x. We got a constant over x to the power of 1. As x approaches positive infinity, that's going to equal 0. Minus the limit as x approaches infinity of 3 of a constant, it's just equal to that constant. And so that property that I initially brought up at the beginning of the video, the reason is because you're going to end up getting a lot of these types of expressions when you're solving these limits. And you're going to see it happen again in 2, 3, and 4. And then you just have this over here. And so notice that what would we end up with here? We'd end up with 4 over negative 3 or negative 4 over 3. And that ends up being the limit for this. And remember, limits at infinity, what do they deal with graphically? They deal with horizontal asymptotes. So this negative 4 over 3 is actually going to be the horizontal asymptote for this function. We're going to talk about that more when we get into curve sketching. But yeah, in case they ask in a question, this y equals negative 4 over 3, that horizontal line is the horizontal asymptote for that function. So answer is negative 4 over 3. So that's the process. That's what you're going to be doing with these kinds of limits. And they're going to get more complex. I'm going to show you in the next video. Sometimes you're going to have to deal with square roots. And there's going to be a couple of sort of additional steps to this method. But for these types, in these formats, that's what you're going to be doing. You're always going to be dividing all the expressions by x to the power of the degree in the denominator, or the highest power in the denominator. All right, so let's follow that same format for number 2. So this here ends up being negative 4 over 3. So we got the limit as x approaches negative infinity of 5 over x squared plus 3x. Dividing all the expressions, first step, by x to the power, the highest degree in the, or the highest power in the denominator, which is 2, right? This is a quadratic here, has a degree of 2. So what we're going to be doing is multiplying the top, the numerator, by 1 over x to the power of 2, multiplying the denominator by 1 over x to the power of 2. Right? So it's like we're multiplying this entire expression by 1. And what will happen, this 5 will be over x squared, this x squared will be over x squared, and then this 3x will be over x squared as well. And then what you want to do is you want to simplify this. The 5 over x squared, that can't simplify, so we leave that as is. Notice x squared over x squared, those will cancel out. And so we'll just be left with 1 at the bottom. And then 3x over x squared. Notice that if you remember how to simplify rational expressions, x squared, that's like an x times an x. So we have 1x at the top, 2x's at the bottom, so cancel out. We're just left with 1x at the bottom. So 3x over x squared is the same as 3 over x. Another way is you have x to the power 1 over x squared. Notice we can subtract here, so we'd have 1 minus 2, which is x to the negative 1, which is 1 over x. So there's the 1x left in that denominator. And now, can't simplify any of these anymore, but now what we could do is we could distribute this limit to all of these expressions, which I'm not going to do. I'm not going to write that out like I did in the first one, but that's what you'd be doing. You'd be using the properties of limits to take this, put it here, put it there, put it there. And after you do that, notice the limit as x approaches negative infinity of 5 over x squared. What's that going to be? Well, notice that's in the format a constant over x to the power of r, x to the power of a rational number. And we said that that's always going to equal 0. So the top, the numerator, is going to be 0. There's no other expressions there. The 1 stays as is. And then the limit as x approaches negative infinity of a constant over x to the power 1, or 3 over x, that's going to be 0. So you're going to end up with 0 over 1, which is what? 0. Okay, so you can take 0, divide it by a number, but you can't take, thought I would mention this, you can't take a number, a constant, and divide it by 0. That would be undefined. And we're going to run into a situation where that happens. But yeah, if you have 0 over a number, that's always going to equal 0. And so the limit as x approaches negative infinity of this function here is going to equal 0. And you can actually think about this kind of logically from a higher level. If you think about it, you have a constant over what? X squared plus 3x. So what's going to happen as x approaches negative infinity, as it gets really, really large? Well, you're going to end up having negative infinity squared, which is a really large number, positive infinity, plus 3 times positive infinity. So you're going to have a constant over a very large number. And a constant over a very large number is going to be really, really close to 0. So when you look at these sometimes from a higher level, it should make sense to you as well. Your answer should make sense. And again, what that means is that this function here, it has a horizontal asymptote at 0. Remember, limits at infinity give us horizontal asymptotes. And it has a horizontal asymptote as x approaches negative infinity. Sometimes you'll have a different horizontal asymptote as you approach positive infinity. In this case, it's going to be 0 both ways. Same thing up here. But not all functions are going to be like that. But yeah, that's the limit for number 2. Use the exact same method. Now, number 3, we got, what do we got here? We got the limit as x approaches infinity of 5x squared minus 3x all over x to the power 3 plus 3x. So we're going to divide everything by what? X to the power of the highest degree, or the highest power rather, in the denominator. The degree is 3. So I'm going to take 5x squared divided by x to the power 3. I'm going to take 3x divided by x to the power 3. I'm going to take x to the power 3 divided by x to the power 3, and then I'm going to take 3x divided by x to the power 3 as well, right? Which is the same as taking all of this, multiplying it by 1 over x to the 3, multiplying it by 1 over x to the 3. And now simplify these. So we'll have the limit as x approaches infinity. 2x is up top, 3x is at the bottom, means we're left with 1x at the bottom. So that would be 5 over x. That simplifies to 5 over x. This 2x is left at the bottom, so we'd have minus 3 over x to the power 2. X to the power 3 over x to the power 3, that's just 1. Those cancel out. And then we got 1x, we got 3x's, so one of them cancel out. We're left with 2x's at the bottom. Right, and now we could distribute this limit as x approaches infinity to all the expressions. What would we get? We get 0 here, minus 0. Notice those are in that format of a constant over x to the power of a rational number. And then we got 1 plus 0. So we'll end up with 0 over 1, which, like in question 2, is just equal to 0. So this limit here is also going to equal 0. And then finally, we got number 4, which I wrote up here. We got the limit as x approaches negative infinity of 3x squared minus 4x all over 3x minus 2. So exact same process. Take all the expressions, divide them by x to the power of the highest power in the denominator, or the degree in the denominator, which in this case is 1. So we're going to take the 3x squared divided by x, take the 4x divided by x, take the 3x divided by x, and then take the 2 divided by x. And now what we're going to do is we're going to simplify these. So notice this x, and then one of the x's up top will cancel out, so we'll be left with 3x for this expression. There's 2 x's at the top, 1 x at the bottom. Right? So before, sometimes we had like 2 x's at the bottom, and then 1 x at the top. In this case, we had 2 x's at the top, 1 x at the bottom. Just wanted to make a note of that. So we're left with 3x, not 3 over x. These x's cancel out. We're just left with 4 up there. These x's cancel out. We're just left with 3. And then over here, this can't simplify, so we're just left with 2 over x. Now what happens is, notice that this limit here is a little bit different, and the reason is because we have this x up top. So it's not like 3 over x, it's 3x. So not everything is in the format of a constant over x, or just a constant itself like it was for the other limits. So what's going to happen here, let's make this substitution. We're going to have 3 times negative infinity minus 4 over 3 minus 2 over negative infinity. And we know that this, it's going to equal 0. We don't have to write this out. Let's just write 0. But this I'm going to write out for now just because it's a little unique. And so what would we end up with here? Notice that 3 times negative infinity is going to be a really large number. So it's going to still be negative infinity. Minus 4, still going to be negative infinity. So this whole thing here is going to be negative infinity over 3 minus 0 is 3. And then negative infinity, a very large number, divided by 3, still a very large number, still negative infinity. Okay, so notice that this limit here, number 4, it doesn't approach a certain number like 1, 2, and 3 approach. Notice here we approach negative 4 over 3. Notice these approached 0. This one here is approaching negative infinity. And sometimes textbooks may even say that this limit doesn't exist. I'm going to actually write negative infinity here. So it's not approaching a certain number. So basically this function, I'm not sure how it looks like right now. I'm not going to spend time graphing it, but what I do know is that as x approaches negative infinity, the y values are going to approach negative infinity. So something's going to happen where it's just going downwards. So whether it's going downwards maybe like this, or maybe it's going to be going downwards like that, there's going to be some kind of shape that I'm not too sure about right now. I would have to go through the steps of graphing this. There's actually going to be an oblique asymptote because the degree of this is 1 larger than the degree of the denominator, if you remember from advanced functions. But anyway, we're not going to be worrying about graphing. All I know is that as x is going to approach negative infinity, the y values are going to approach negative infinity as well. So they're not going to approach a certain number like we did in 1, 2, and 3. So this one was a little bit different, and the reason was because we had that x left over. We didn't have like a constant over x, we had a constant times x. So when you made that substitution, you're going to get negative infinity, and sometimes you'll get positive infinity here as well. Now, one thing I want to mention, a little trick for these kinds of limits here, you may remember from advanced functions when we were graphing rational functions, is that you can actually look at these limits as long as they're in this format and know what these answers are going to be without doing all the algebra, which may help you. And basically, there's going to be 3 different cases. So either the degree of the numerator is going to equal the degree of the denominator. So like in this case here, notice the degree of the numerator is 1, the degree of the denominator is 1. And when this happens, this limit, as long as it's positive or negative infinity, this limit, remember this is for limits at infinity. So they got the x value has to be approaching plus or minus infinity. If this happens, the answer is always going to be the leading coefficient of the numerator over the leading coefficient of the denominator. So what's the leading coefficient of the numerator? The leading coefficient is the coefficient that's in front of x to the highest power. So it's 4, and over here the leading coefficient is -3. So it'll be 4 over -3 or -4 over 3. So notice how we ended up getting that doing the algebra. So that's a case that can come up. You could also get a case where the degree of the numerator, I'm just going to use short form here, is less than the degree of the denominator. And if this case happens, let's put an underline on all these. If this case happens here, the limit's always going to equal 0, because that denominator is going to increase quicker than the numerator. And when that happens, you're going to have a number over a very larger number, which is always going to be 0. So notice here, we had a 5 up top. What's the degree of just a constant? The degree of that is just 0. It's like x to the power 0, which is just 1. And the degree here is 2. So notice the degree of the numerator is less than the degree of the denominator. What did the limit equal? 0. Same thing here. The degree is 3 in the denominator. Over here, the degree is 2. Degree of numerator less than the degree of the denominator, 0. Right? So that's always going to hold. Remember, it's got to be in this kind of format. So we're going to be doing limits at infinity over the next couple of videos where we're going to be dealing with square roots and stuff like that. Then these properties are not going to hold. These properties only hold for these kinds of limits where you don't really have any square roots. You're just like have a bunch of expressions without square roots. You have polynomial expressions in the numerator and denominator. That's when these properties are going to hold. But when you start having square roots and stuff, it could start getting a little bit more messy. So you don't want to depend on this all the time. This is just kind of like a side note that I want to make. A trick that you can sometimes use where you look at a limit, you know before even solving it that it's got to equal 0. So when you do the algebra, you know what you're getting to. And then finally, you could have the degree of the numerator being greater than the degree of the denominator. And when that happens, notice here, degree 2, degree 1. When this happens, what's going to happen is that limit's going to go to either plus or minus infinity, right? So there's not going to be a horizontal asymptote. That's another thing to mention here. There's no horizontal asymptote for this limit. It's not approaching a certain number. So there's a horizontal asymptote here, here, and here, but over here, there isn't one. For there to be a horizontal asymptote, it has to approach, the y values have to approach a certain number as x approaches plus or minus infinity. So anyway, thought I would just mention these rules as a side note, but remember, apply these rules only when it's in this kind of format where you got like polynomial functions over polynomial functions and there's no real like square roots to deal with. And in the next video, what I'm going to do is limits at infinity again, but now I'm going to make the expressions in the numerator and denominator a little bit more complex. They're going to contain square roots, so I'll show you how to deal with those.